I'm very excited that you're back here if you've attended the previous sessions in this track. Otherwise, welcome to the Enterprise Architecture track day 2. This double session will be slightly different than all the other sessions we've seen today because it consists of many multiple different speakers. And the topic is kind of enigmatic, I think. So I will not introduce that. I will let the double session host, Kevlin Henney, introduce what this track will actually be about. But what's interesting here is that we're experiencing a recursive scenario, because first I'm here introducing Kevin, and then Kevin will introduce me back and other speakers as well. So if you see me here, don't assume I'm the track host all the time, just a warning. And then, but currently I'm the track host, so I need to remind you to vote and also ask questions through the app, so we can take them in the question and answer session. Kevin.
Okay, thank you very much. Live, good. So we were discussing what is the goal of this session. We were discussing it in the break, and Ola Bini came up with the great phrase, "This is architectural dim sum," which hopefully, we're about the right time of the afternoon that you might start thinking about eating something else. So what we're going to look at is sort of a few little samplers, a few little ideas in and around enterprise architecture, or to be precise, some of the ideas that people tend to consider. And they say, well, yeah, that's fine. I see what you're doing with that technology or that approach. That's great, because we hear that for your startup. We understand for your small company. We understand. But we can't do that where we are, because we're enterprise. You know, that sounds great, but it's not for us. Sometimes the word enterprise has a negative connotation. So what we're going to try and do is give you a sampler of the fact that actually we can think outside that kind of classic enterprise box, as well as there's just the gratuitous use of Star Trek references all the way through. I mean, who can say no to that? So my major disappointment actually was the fact that we were unable to get Catherine Kirk, who is at this conference, to be on this panel, because that would have been beautiful. Her sister's surname is Spock. I kid you not. Okay? I kid you not. You know, hand on heart, the whole deal. Okay. Written a couple of books with the word architecture in the title. That's got to mean something. But that begs the question, what is the meaning of this stuff? So whenever you're confronted by a word, you can either go and look at the blogosphere or go and look at your dictionary. So I decided to go and look at my dictionary, because we use this word. It's become very, very popular in the last decade and a half. What do we mean by this? This word appears everywhere. Is it just another fancy way of saying architecture? What does it actually suggest? And does it suggest things that we recognize when we talk about enterprise architecture? Or are we a little bit surprised? So the invisibility on this is very clever. Oh, there we go. A project or undertaking that is especially bold, complicated, or arduous. That sounds familiar. Yeah, we can buy that one. Readiness to engage in undertakings of difficulty, risk, danger, or daring. That's interesting, because that's not always what we think of when we think of enterprise architecture. We don't think of people taking risks and being daring. There's a suggestion here that perhaps we should be a little more adventurous. We don't tend to think of adventure in the context of this. People are very averse to risk in enterprise environments. It's often a very conservative, steady-as-she-goes way of doing things. I love this one. I wasn't going to include it, but I thought I have to. A design of which the execution is attempted. Because that definition suggests, well, we'll give it a try, but we're not expecting it to work. We're going to attempt it, but, you know, really, it's just going to be another big enterprise failure. A commercial or industrial undertaking. This sounds familiar. Likewise, a firm, company, or business. Okay, so that seems reasonable. And then we have a unit of economic organization or activity, which tells us that actually perhaps the word enterprise doesn't necessarily mean large. It really can be divisible into the smallest fractions. But if you're like me, well, I feel sorry for you actually. No, if you are representative of a particular group of people who end up in software development, you still can't help but think, oh, he said enterprise. There's only one thing that can come to mind. And it turns out that this is actually a useful perspective, believe it or not. It's a very majestic, beautiful picture there. The twin nacelles there, holding a stable warp field. What makes a stable warp field? I'll come back to that. So, what do we mean by this word architecture? We figured out the enterprise bit, but the architecture is going to span many things. It's going to span people, it's going to span hardware, it's going to span departments, it's going to kind of touch on lots of fictitious units, if you like. But it's also going to touch on roles and software. So I came across this a number of years ago as a definition, and I want to present it to you not because I agree with it, but because I don't. So written in the late 1990s, a piece called Software Architecture Needs Blueprints. In the developed nations, the architect's responsibility is to provide adequate blueprints, work with the construction firm to make sure they are understood, work with building inspectors to validate conformance to the blueprints, then make formal changes to the blueprints as new requirements are identified and as construction problems are discovered. No shortcuts in this workflow would be excused or accepted. This analogy applies precisely to software architecture. I'm fond of noting there are only two things wrong with this, the first paragraph and the second paragraph. When we look at this, there's something interesting going on here. If we look at the first paragraph and we read it carefully, who is the most important role? This is the bit where I actually ask you a question and you tell me the answer, yeah? Thank you very much. We're going to come back to that. I was after a person, but you are correct in identifying that. That's a what? Yes, blueprint. That's top. Yeah, I'll come back to that. But who as a person? The architect. This is a slightly self-serving piece. Yes, of course the architect. We put him on a pedestal. It's important. The architect, center of the universe. Who's missing? The rest of the universe. Or let's actually talk about it, the customer. Where's the customer in all of this? Where are they? They're invisible. And if you actually ask any building architect, and indeed a good number of software architects, and a number of people who would quite happily brand themselves and self-publicize as enterprise architects, one of the things they often talk about is the relationship to the business, the customer. And they're not being fed information, you need to say this. They actually mean it. They consider themselves to be a bridge between the world of the technology and the world of the business, the customer, and what have you. In other words, that's essential. You take that away and there's nothing left. So it turns out this is not a true statement of the relationship that building architects have, and it's also not a valid one in this case. Now, to your observation, there is the battery's dying. Okay, we'll change that. There is the observation that blueprints are the most important thing here, which is kind of interesting. I came across a nice little piece in Bill Bryson's book, Troublesome Words, a book on word usage. And he said, blueprint as a metaphor for a design or plan is much overworked. If the temptation to use it is irresistible, at least remember a blueprint is a completed plan, not a preliminary one. And this was written in the early 1990s. He had not heard of enterprise architecture, and he was not talking about enterprise architecture, but I think he knew. So if you want blueprints, there you go. That's completed. But really, there is a nice little quote I picked up. There's lots of definitions of architecture. We could fill a whole talk just defining it. But this is a definition that was given to me by Tom Gilb. A couple of weeks ago, I was at Java Zone in Oslo. I sat down with Tom, and he said, what do you want to talk about? Tom does this. What do you want to talk about? Here's a number of things we could talk about. And I said, you know, of the things you're talking about, let's talk about architecture. And he said, oh, have you ever seen my definition? And I said, I'm not sure I have. So he showed me a thing, and I said, that's brilliant, because I've been trying to push this idea to people for a long time that architecture is a hypothesis, but it's much better when you can quote somebody else saying it. So I'm quoting Tom. Architecture is a hypothesis that needs to be proven by implementation and measurement. Now, what is important about this is that it gives us a very different relationship with the idea of what an architecture is. It tells us that an architecture is not necessarily a set of fixed ideas, or should not be considered that way. An architecture is contingent on reality. It's the idea of you're always asking a question. Let's try this. We believe this will be appropriate. It suggests you need an empirical development model to back it up. So in other words, the architecture and the process are kind of tied together. It suggests that you are always in the position of asking the question. Is this appropriate? Does this work for us? Does this meet our needs? Importantly, it's also a function of time. So although we often say things like, hypothesis in science, normally things stay fairly fixed. But what we're talking about here is a changing situation. Just because it was a good architecture 2 years ago does not mean it's going to be a good architecture in 2 years' time. So this is an ongoing hypothesis that we must test and confirm. Now, conveniently enough, that allows me to talk about, yes, the Enterprise. Because this is, was going to be a spacecraft called the Enterprise. This is the first space shuttle built, the first orbiter. It was designed to test the hypothesis that we have a design that actually works. And for those of you not familiar with the dynamics of the now retired space shuttle, after it re-enters the Earth's atmosphere, it becomes the world's heaviest glider. It has no engines. Those 3 things sticking out the back, that's space stuff. That gets you into space. It moves you around space. But once you're back in the atmosphere, you're just gliding. Now, if you look at that, you're thinking, yeah, that looks just like a glider. It's got that kind of... You might want to test this one out first, yeah? Which is what they did. They wanted to test out the balance against the external tank and the solid rocket boosters, that the whole structure would balance. They wanted to test the airframe. So basically they built it. This is it's basically a full space shuttle, except for the heat shields and the engines. Those are appropriate weight. Their original plan, NASA's original plan, was that this would be refitted and it would be used as an orbiter. But what they discovered as a result of experimentation was that it would cost them more to do that than to build another one, the Challenger. So in other words, they actually did the hypothesis measurement thing. Now, it also tells us that we should think a little bit larger. This is a design for the Enterprise. This actually comes out of some current work that NASA are doing. What are they looking at? What is this spacecraft apart from very, very cool? What is this spacecraft? What is it built on? It is built on the... Come on, speak to me. Oh, there we go. It is built on the idea of warp drive. Yes, NASA actually has a warp drive program under research. It's based on a model by a guy called Miguel Alcubierre drive. He formulated this in 1993, doing some terribly devious things with general relativity. And actually, this theoretically could work. When could it work? Well, it could actually work in a few centuries' time. Those 2 big rings, that's how you create a stable warp field. So NASA are actually going to deliver this in the next few years? No, like I say, this is, if it works, it's a few centuries away. But they are looking ahead. They want to try stuff out. This is the idea that you should be invited in an enterprise environment, quite literally, to experiment. Because an enterprise is not simply something that exists in the present tense. People often look at an enterprise as, it's here now, it was there then, and we have a few projections. The one thing you can guarantee about those projections is they will be wrong. And you need to experiment wildly, and that should be encouraged. It's okay to think. I mean, this is about the ultimate in thinking outside the box that you're going to get. So I'm going to bring you back down to earth in order to introduce our next couple of speakers. There's a little thing that I came across a number of years ago, the reference model for open distributed processing. It's an ISO standard. It's formulated in the 1990s. Doesn't leave much of a footprint in people's minds anymore, except that it had this one very nice way of looking at things. In order to answer the question, what is an enterprise architecture? What they did is they said, well, look, architecture, it's big, it's complex, potentially there's lots of different ways of answering that question. So perhaps there are different perspectives on it. And rather than hold to one perspective, because you speak to some people and they say, oh, the architecture is the technology, and they attach to that. Other people, they attach to the business purpose. Other people are rooted in the component model. Other people always think of the data first perspective, and so on. And all of these perspectives are valid. And it's a very simple way of looking at it. It's like these viewpoints are literally that. It's as if you held up a physical object and you said, when I look at it from this angle, head on, this is what I see. When I look at it from this angle, from the side, this is what I see. And what we're doing here is we're saying we can hold up the idea of an architecture and say, what is the purpose of this thing from a business perspective? That's the enterprise perspective. We can rotate it around and say, yeah, but I now want to talk about the information model that this embodies. What is the information universe that such an architecture will inhabit? What does it actually need to know in order to operate? And that's not the equivalent to your data model. Your data model can be derived from it, though. Computational, that's where the code, the components, and all the rest of it live. The engineering perspective is what we would normally consider to be the architectural styles and the infrastructure, but not necessarily the specific technology choices. So when you are asked the question of, like, what is this architecture? These 5 viewpoints, they don't give you an answer, but they give you a focus through which you can answer. So on that note, I'm going to introduce, we're going to do that recursive inception kind of thing. I'm going to introduce Eva to talk about the big data thing, which often people think of as being divorced from their classic view. And I must warn you, it's not behaving very well. Sorry.
I'll work with it. Yes.
Okay, you talk, I'll...
All right, so I'm Eva Andreasson. I work for a company called Cloudera, and we work in the infrastructure vendor space, and we work with solutions around big data. But I'm not going to talk about our products here. I'm going to talk about the architecture. And Kevlin and I had interesting, what would you call it, Kevlin? Debate? Discussion? Okay.
Sadly, we had to come down here and talk to you guys. I mean, we could be out there just...
This is very compressed debate about if, you know, all these perspectives that was so nicely shown in the previous slide, if it's actually technology driving architectures, or if it's actually business requirements driving architectures that then lead to technology choices. And I think it's a very interesting thought to think about, that sometimes new technologies come out that open the ideas for new architectures, especially in the data centers where I'm involved. And on the other hand, there might be some macro trends in the market or business needs that actually drive new thoughts about how to address them that drives technology. So there's no one way of looking at architecture, that's for sure. I don't know where we ended up in that debate, but it's interesting for the audience perhaps to think about. So big data, we all probably know where it comes from by now, but there has been a tremendous innovation in device technology, not only cell phones and laptops, but also in clothes, glasses, watches, your car, your home equipment. Everything is generating all these log data, not only about the health stat of those devices, but also how you interact with it, how frequently you use it, in what context, what part of the product are you actually using. And all this data is streamed back to the businesses to better form products and services forward, and also improve different optimizations. Another driver in the market is, of course, we do a lot of business online. And I think we do most of our business online today, actually. And this has generated a lot of new innovation around data types, new technology coming out to serve these different businesses. And all these transactions need to be handled, and it's a bigger volume than ever. A third driver in the market is the social activity we have online. We live our lives online in a much wider extent, and we leave these traces behind about who we are, what we like. And this is a whole gold mine for businesses to dig into, to understand customer segments and users better. And all these drivers in the market has led to new technology innovation. So that it's the path of market drivers putting pressure on traditional systems and has opened the door for a lot of disruptive technologies out there. But what we might have forgotten to reflect upon is that it has also changed how organizations think, how enterprises think. It's about all this data and deriving information from it. We've done it for many decades already. But as more data comes in and more different needs in the organization to access this data has grown, organizations are thinking about big data within their companies as well. So how do we keep communication, and how do we keep truth about what's going on, and how do we coordinate the different teams within our organizations based on all this data that we have in our enterprise today? So corporations I sit and talk to with their strategy teams where we plan out the next 2-3 years of data management, they are talking about being fully information driven, meaning every level in their organization should have access to data and make decisions on it, and it should be the same data. And how do you make that data shareable to serve a variety of audiences that needs to make independent decisions if we are to be agile and flexible with new business demands, market trends and drivers? How do we make our organization more independent but still making the right decisions on their own? Well, if we could give access to all this data to all the levels in the organization, if every decision is information driven, we could potentially get there. It's a hypothesis, right? And it drives an architecture. What kind of architecture? Well, today, our enterprise data centers or deployment parks look like this. It's a variety of backends, a variety of audiences trying to access different parts of the data in those backends. It's very normal. It's a dynamic growth of deployment models, different systems serving different needs over time. It's very normal to see multiple copies of data, partial data being served in a very heterogeneous environment. But how do you become information driven with this kind of deployment architecture in mind? How do you allow a shared data access? So what has been effective with these market drivers and this new kind of thinking of how do we make data accessible to everybody to act independently on it, has driven a new concept, a new architectural concept in the data center called the Enterprise Data Hub. It's one place where you gather all this data that the hypothesis, the thought, the vision is, okay, we want all data that we can collect about our customers, about our devices, about people and segments, to do better business, to drive our information-driven business decisions. We need to collect all that data, have one true set of it, and then natively process it and serve it to a variety of audiences, because we can't live with the complexity of this. We can't rely on that every portion of our organization has access in a timely manner and has the truth. This also generates more creativity, more innovation, more independent innovation on what questions to ask in different parts of our wide organizations. So it actually enables more agile, more independent data-driven decisions. Of course, other systems are still there. It's not a rip and replace model. It's an evolution of the data center architecture. And it's interesting, I think, to just spend some time and reflect how market drivers have actually changed the way we think about architecture as well as driven new technologies. So I, of course, work with one of the technologies in the space, Hadoop, and all the ecosystem components around it, and how we envision in the Hadoop world to serve such an enterprise data hub is, of course, through the Hadoop ecosystem. We drive that open source community forward and try to think about how these enterprises that have these needs and these strategies can be served using these technology components to build their enterprise data hub. So this is a kind of a map, again, a hypothesis of how to serve that architecture. So this is another view of an enterprise data hub architecture where you see data needs to be either served as a file system or some kind of table level structure model to fit into the data hub deployment model. And then you have to have a shared resource manager that can control what workloads can access what data or what portion of the resources in a timely manner. You have to have security, you have to have management, you have to have governance and data lifecycle management. None of those requirements have gone away. And then you have to have all these different workloads to serve the different audiences. So if you keep this image in mind and then go back to this, instead of having one very distributed, complex, heterogeneous model to serve these different audiences, you have one unified storage, but different tools for different audiences. That's the whole idea with the Enterprise Data Hub. And Hadoop, as a disruptive technology, fits in to serve this. But so does other technologies. It's not the only technology option, but the architecture is where organizations are trying to get into their data centers. So I think that was it. This is a reflection on how trends in the market also affects architecture and not only technology.
Thank you very much, Eva. Yeah, thank you very much. Right, okay, so we'll be taking questions at the end of the session. Related, I'd love to make a joke about slightly more diffuse, but actually no. I'm going to ask Randy Shoup here to talk about the cloud, and provocatively, because again, this is one of those areas that people are often thinking, oh, the cloud, that's all very well for that kind of business, but we do this, we're special, and perhaps it doesn't apply to us. It's a great buzzword, and we'll leave it at that. And actually, there's more to this than meets the eye. Randy.
Great, thank you. Excellent. Great, so I wanted to talk a little bit about why some maybe surprisingly large and surprisingly old-style enterprises in at least North America are starting to look at leveraging cloud technologies for doing their IT. So some of the obvious reasons that we probably are all familiar with about why organizations might embrace the cloud. The first obvious one is provisioning speed. So many of us may still be experiencing this, but certainly all of us who have gray hair or no hair, as I do, have experienced the idea of waiting weeks, maybe months even, for compute resources that you need to do your job. So the concept, the idea that we might be able to get compute resources in minutes or seconds rather than in days or weeks or months is extremely exciting and extremely empowering. The second idea is related to that, is the idea that we might be able to auto-scale our services or our compute resources in response to load, right? If we don't have to wait weeks for a resource, if we can spin something up in minutes or seconds, now instead of defensively over-provisioning, predicting ahead of time what we might need 1 year or 2 years out, we might be able to follow the curves of our actual business. Related to that, and this is mostly if you're leveraging a public cloud situation, from the perspective of really any business, there is near infinite capacity available in the first-tier cloud vendors, right? So if you're leveraging a first-tier cloud vendor like Amazon or Google or Microsoft, from your perspective, and honestly, no matter how large you think your organization is, the size of the cloud in relation to your need for machine resources is nearly infinite. And so again, there's no need for you to prospectively reserve capacity in face of ahead of needing it. You can react to the changes up and down daily or weekly in your business and only acquire the resources when you actually need them. And of course, the related notion here is paying for what we use, right? Again, rather than paying for the peak of the peak of the peak, plus 50% for, extra margin of error, and paying for that all the time, we'll only hopefully pay for the resources that we're using at the actual moment. So rather than paying for the peak, we end up paying for the average, which in most of our use cases, in most use cases I've seen in lots of different companies and enterprises, we typically tend to use our resources at maybe 10%, 20%, something like that. So imagine how much waste there is that we could give back to the rest of the world and not pay for if we were able to follow the curves rather than provision for the peak. And then, of course, a related notion, particularly for those with a finance background, is, I'm coining this term and I hope it makes sense. I don't want to take on the utilization risk. So what I mean by that is when I buy a piece of hardware, I'm essentially buying the risk that I sort of have the responsibility to use it 100% for as long as it's useful, right? And I'd much rather let Amazon or Google or Microsoft take that risk and pay them a little premium for that. So this is called option value in finance. Pay them a little bit of premium for taking on that risk, and again, only pay for the stuff that I'm actually using. So this is sort of the obvious reasons why really enterprises, large or small, are thinking about the cloud. There are some less obvious reasons. The first is something that I'll call instance optimization opportunities, and that's quite a mouthful. But what I mean there is that the cloud is that when I buy a piece of hardware, I buy it with a particular configuration, right? So I'm going to buy it with 16 cores and 128 gigabytes of memory and some number of spinning disks and some number of SSDs. Like I'm buying a physical system which has a particular physical shape, right? A particular physical shape. The cloud vendors have lots of different shapes I can choose from. And again, this idea that I can provision things and give them back and maybe only pay for 1 hour of usage or 10 minutes of usage or whatever, depending on your vendor, I can choose my shape and I haven't had to think of it ahead of time, right? I can try the shape that's the 16 core, 128 gig of memory, and if that works well, then perfect. Maybe I need a smaller shape. I need an 8 core shape, or I need a 64 core shape, or I need a 4 or a 2 core shape. And I get to play with that in the public cloud basically at no risk, right? I don't have to have bought the machines and installed them in my data center and configured them and so on, powered them up, put them in racks in order to be able to test things. That's wonderful. The other thing, and it's maybe impolite to say, but I've lived this on both sides of the fence. The service quality of people who do this for a living is really extraordinary. And Amazon and Google really know how to run a data center. This is essentially half of their business, right? Each of them has other halves, right, where they make a lot of money and have for a long time. It's actually how they were able to fund all these data centers that they then rent to us. But they really know how to run a data center. So, and they experience failures at a rate and at a scale that are far beyond what most of us see in our enterprises. So the stuff that you're essentially renting from them is extremely battle-tested, extremely highly automated and optimized. And in particular, the thing particularly for Amazon and Google where I'm more familiar, the networking infrastructure in the public cloud vendors is far and away better than what I've seen in most enterprises. Each of them has been pushing, it turns out, and mostly in the same direction for the last 5 years towards software-defined networking and full bisect bandwidth anywhere in the data center to anywhere else in the data center. It's really something that most people don't have access to in their day-to-day lives, even if the enterprises are multi-billion-dollar organizations. So you still want to own your own data center. Well, think about the economics here. And I want you to, don't think of this as sort of aggressive or provocative, but ask yourself these questions and answer it in the quiet of your own mind. Can you buy hardware more cheaply than Amazon or Google or Microsoft? Are you buying chips in the millions and the tens of millions a year? Can you operate your data center more efficiently than they can, right? Can you have, a team of 7 or 10 people operating tens of thousands of machines? Can you achieve better resource utilization than Amazon and Google, right? One of the reasons why they're able to operate things more efficiently is not just because they have low cost of hardware, which they do, not just because they have very good, highly scalable, efficient operations, which they do. It's because they have an extremely diverse set of workloads where the spikes of one application end up filling or get filled in by the spikes of the other application. Is it making sense what I mean? I really should have a picture for this. But they have such a diversity of workloads that they can run everything very, very close to full utilization, full appropriate utilization, exactly because they have so many different workloads that they can slot into those empty spaces in the infrastructure. So they're not, they take that utilization risk, but they're able to deal with it because they have such diversity of workloads. Resilience to breaches and failures. So a very legitimate first order concern about enterprises moving into the cloud are things like security. Security in relation to physical security of the data center, virtual security, if you like, for the software that's running. And again, you have to ask yourself, is your security team as well practiced as Amazon's and Google's? They have to defend them. I mean, they're the biggest targets in the planet, right? And they have to be able to defend themselves against that. And partly what you're renting when you rent machines from them is some of that expertise. Can your teams manage machine failure, disaster recovery, redundancy at the same level? And the answer is maybe yes, right? If they are, great. I actually want to work with you and for you. But think carefully about what the answers are here. And then the final question is about global footprint, right? Even the most global of enterprises probably doesn't have 100 data centers around the world. And so the question, if part of the reason that you've built compute infrastructure is that you want to deliver things to customers or employees that are all around the world, located on every continent, you should ask yourself, do you have a sufficient global footprint that has data centers on all the continents, plus the additional edge points of presence that are close to where the population centers are, plus the peering relationships that the large internet companies have with the large internet pipes, right? Anyway, so these are all questions one might ask oneself if you wanted to build and operate your own data center. So the final thing is, again, totally legitimately, hey Randy, come on, I work at a bank. Well, there are a number of banks actually that are using public cloud today. So I was pleasantly surprised to read, and this is actually several years old, I didn't realize it, but I was pleasantly surprised to read that 3 of the top 5 banks in Australia are all leveraging Amazon Web Services for a bunch of their compute. Also, I recently learned, I think this was again a year ago, that I'm forgetting the actual Dutch word for it, but the Netherlands Banking Authority, which is the regulator of banks in the Netherlands, has recently certified, or a year ago, certified that yes, banks in the Netherlands are legitimate from security and regulatory concerns, legitimately can leverage the public cloud for a lot of their workloads. And many others that we can't talk about publicly are actually actively piloting and experimenting with this technology right now. And also, so even if you believe that, as would be legitimate, like, look, I do personally identifiable financial information. There's no way I could ever put that in a data center that I don't operate myself. Great. Even if we grant that, think carefully about what the majority of computing is at your bank, for example. The majority of the computing at your bank is actually not banking, right? It's actually not the regulated financial operations. It's not about talking to a financial exchange or a stock exchange or commodities exchange, and it's not these regulated operations. So even if you believe that most of those things need to stay in a traditional data center operated by employees, great. But think carefully about whether it might be possible to move some of your other workloads there. You'll be able to take advantage of all these economic forces and maybe have a lot of fun doing it. So my last little maybe provocative set of statements is, I've been talking to a bunch of sort of analysts and, various folks about cloud for a while. I assert, and this is only my assertion, but I'm starting to believe my own, hype. I believe that the 2010s of computing are a lot like the 1910s of electric power. So Henry Ford, who was one of the very early automobile manufacturers in the United States, famous for essentially inventing the idea of an assembly line. When he started building his cars in around the 1910s, the very first thing he needed to do when he wanted to build an assembly line in a car plant, an automobile plant, was find power. I mean, he literally had to go look for a river where he could sit a water wheel so he could get electric generation capacity so then he could power his assembly line. Now, we don't do that anymore. anymore, right? Because most of us live in areas where we get sufficient electric capacity from the electric grid. So, you know, for all intents and purposes, you know, we plug into the wall and we're good. And so I assert that soon it's going to be just as common for enterprises to operate and run their own data centers as it is for enterprises to operate and run their own power generation utilities. And there will always be exceptions, right? There are enterprises that run their own power generation because they need to be a backup to the grid, because they need to be survivable in the face of the worst possible disasters. But I think it's going to be less common than it is today. So that's all I have to say about this particular section. And again, we'll take questions at the end around the break.
Thank you very much, Randy Shoup. And conveniently enough, that around the break bit, let's have a nice pretty back screen. What do you want? Do you want Star Trek image? You want the proper enterprise image?
There we go.
No, do you want that? You give me your preferences and I'll put that up. Let me think. Where are we? We want that one. There we go. That's what we want. Oh, no, we don't. We don't want that one. We want that one. That one? No. No. Somewhere here. Over the rainbow. There we go. That's nice. I like it. It's got a very calming feel. Good. Now, we are near the break. So, Eva can... pull you back. Right, so, questions. So we've compartmentalized the questions, and we're going to throw you out the airlock in just less than 10 minutes.
We have one online, actually. And it's not just, you know, it's just one question, and it happens to be for me. So
That's good, because my eyesight really wasn't doing the right thing at that point. Not Geordie LaForge.
So it says, please post through the app. This is track host Eva. Please post questions through the app if you don't want to, you know, ask in front of everybody. Now back to me. So the question is, won't an EDH become a new bottleneck like enterprise service buses turned out to be? Very good question. So that states, you know, a requirement. It has to be linearly scalable or better, right? So whatever disruptive technology is evolving out there or coming up in the next few years, of course you need to think about how to scale in a distributed fashion so that we don't come up with the same situation that we learned from. So very good reflection and question. Thank you for that one.
And it shows the app works. Okay, so any other questions, thoughts, reflections for Eva, for Randy, even for me? I don't know.
So I have one for Randy. Is it okay that I ask a question?
I don't know.
So
should we vote? Is that okay? Yeah, good, fine.
All right. So, you know, I work in Hadoop land, and over the last 2 years, cloud and Hadoop has come together more and more. But I'm interested in seeing your trend thermometer. Like, where are companies today when it comes to actual production deployments in the cloud? The average company, if you will. I know you're talking about, yeah, you should be there, but where are they?
So I'm not going to assert should or not should. I mean, everybody needs to make the appropriate trade-offs. Just because it's cheaper doesn't mean it's better, but it is increasingly getting cheaper and faster and equally, if not more secure, et cetera. So it's well worth thinking about and continually thinking about, even if you decide not to do it at the moment. Yeah, so where are they? I mean, the answer is it depends, right? So correctly, large enterprises are typically late adopters of this type of disruptive technology. That's correct, because there's way more to lose if it doesn't work out, right? There are pretty large enterprises, well, depending on what, you know, we can put them on, where we put them on the, you know, unicorn versus horse scale we can argue about, but certainly all the largest of the internet companies that independently invented these ideas, right? Google built its cloud for its own purposes. Amazon built its own cloud for its own purposes. Similarly, Microsoft, similarly, eBay, similarly, Facebook, Apple, Twitter, ... So, and I guess the way that I say back, you know, when are large enterprises or, you know, traditional enterprises going to get there, you know, the unicorns of today become the horses of tomorrow, right? It wasn't too long ago that a bunch of these very large-scale enterprises today were young startups, right? So, there you go.
Yes.
Yeah, right. Thank you for that question. So I'll repeat it. The question is, Randy, you're an American and so are all the cloud companies. isn't the NSA
Slightly rephrased, but yeah.
isn't the NSA going to be looking over my shoulder? Yeah, that's a real serious concern, and I'm glad you raised it. It was actually the very first concern when we gave this exact talk in Copenhagen, so it's clearly on everybody's mind, as it well should be. The cloud vendors are not unaware of this. So for both the cloud vendors that I know well, that's Amazon and Google, both of them have European data centers, and the data that lives in European data centers does not ever leave Europe and the protection of your data privacy laws without your consent. So it doesn't magically, secretly, even though there are data centers around the world, neither of those companies, exactly because they don't want to violate your data privacy laws, and because exactly you are correctly should worry about them, as we all should, by the way, no matter whose passport we carry, won't leave Europe. So subject to all the data privacy regulations that you already have.
That's your opinion. It doesn't happen to be the US government's opinion.
It's not just I don't have anything to sell. It's not a sustainable business for the vendors if they can't meet your guys' needs.
There was actually a ruling currently in New York that some data in Ireland should be sent to US because it was part of some investigation or it didn't have anything to do with US.
Yeah, I don't know.
The judge said yes, I think they'll take it further.
Let's say it this way, that public cloud isn't going to live very long if it doesn't meet everybody's proper needs.
I'm going to jump in with a question here,
Please.
and then we're going to take your question. What is going to be the impact, with big letters, impact, to the average person in the first world of all these services moving so commonly to the cloud? What changes for regular people?
Wow, I hope just things get faster and cheaper. I mean, let's ask the same question with electrical power. What happens when all of a sudden individual towns or municipalities aren't running their own power generation, but it's more centralized? Obviously on the plus side, in the 99% case, it's better and more efficient and more cost effective. Obviously, we shouldn't forget that we live in a world where failures happen, and so we have to be sensitive to, when there's a centralization, we have to be sensitive to not being a monoculture and be able to survive lots of different types of failures. But we, the broader we in engineering and science, have decades of experience in doing that. I guess the other thing, I think, from the perspective of, a user myself, the more computation that's less expensive and more easily auto-scalable, again, makes things cheaper for me, but also makes things, lower latency for me, because again, the global footprint of a lot of these companies is much larger than most enterprises are able to afford. So when I go, for example, as I have just done in the last several weeks, from the San Francisco Bay Area to Rio de Janeiro to continental Europe, I have extremely good latencies to all the applications, exactly because more and more of the things that I use every day are sited or at least edged close to where I am. So that's a nice property.
Yeah, and I might add to that, if the average person, in this case, it refers to the average engineer, I think all these services and more access to cloud environment will help engineers to experiment more. They don't have to wait for a long procurement process to get some hardware, to try some new things. They just spin up a cluster and try things out and do proof of concept. I think it will enable a faster development process or agile architecture readjustment process, if you will, to tie back into architecture as well.
Yeah, and just quick on that one sentence. I recommend to everyone to see Adrian Cockcroft's talk from an hour ago. He's actually sitting in the back. Hey there. An excellent talk talking about how to design organizations for agility, and there are many interesting points in there, wonderfully stated as always. But in particular, the enabling that cloud and very rapidly infrastructure that's able to rapidly spin up and down is a huge force multiplier. Orders of magnitude faster for developers. So it's a lot faster and a lot more fun.
Yep. That's a hell of a sentence, really.
There was one last question here,
question.
and then we'll go for a break. And you, of course, come up and ask more questions if you want. But
I don't know if it's a question or more of a comment.
do you want a mic?
We can repeat.
Yeah, okay.
So my comment is that if you look at a lot of people nowadays actually start to go back to generate their own power because the big electrical companies increase the prices, having a monopoly, and then you get back to exactly, like it was 100 years ago. I would rather have my own power, and be independent and off the grid because it's more cost effective. So again, going to the cloud to be cost effective would make the move again from the cloud in maybe not 10 years, maybe 100 years, or I don't know. But it's still, I don't think it's still.
No, that's perfect. So just to say back, he makes the excellent point that in electric, so Randy, your analogy isn't perfect, or maybe it is exactly perfect. We'll find out in 100 years. Centralization was the perfect thing to do for power generation in the 20th century, and now we're starting to move with wind and solar and residential electric power, residential generation, that it actually has become, because of technology changes, much cheaper for me to generate my own power potentially, depending on where I live and the sun and the wind and so on. That's great. So yeah, in 100 years that may be true of computing, but it's definitely not true now.
Just a thought on that. It's not the same. It's the same but different. It's a matter of perspectives. All right, so 100 years ago, this is what people were doing with electrics. You had to do everything. And then it went centralized. But it wasn't just centralized, it went centralized. And now we're back, but we're not in the same place. Because if I want to go off grid, I don't have to do everything. There's a whole commodity market. If I want to use wind power, I don't have to construct from raw materials, from scratch, the technology that I will use. If I wish to channel solar power, again, I use somebody else. So that, I think, does apply precisely to computing, and it may be less than 100 years. We tend to work on different orders of magnitude. So I think you're right, but I think this room, see you here, 2024, at about 3:30. Okay.
Thank you, everybody. Don't forget to vote, and we hope to see you after the break.
Yeah,
So
and after the break, we have Randy, and we'll have Ola Bini, and we'll be talking the tech side of things, microservices and polyglot programming. Are we there? Yeah, we're there. Marvelous. Right. Continuing our 5-year voyage. Actually, I'm going to depart from all the Star Trek-y stuff for a bit. My kids thought it was absolutely brilliant. It's just like, Dad, this is work, is this? It's like, yep, that's it. That's what I'm doing. I'm just Googling pictures from Star Trek, and that's great. Okay, so let's go somewhere else. Let's pick a slightly unusual image. This is a book, Design After Modernism. So it's a lot of, I came across this indirectly via Jim Kevlin, who picked on one of the essays in here, and I thought that's kind of interesting. Found this book and found another essay that was of immense interest. A City is Not a Tree, by a chap called Christopher Alexander. Now, depending on your background and your interests, you may be thinking, that's funny, that's the same name as the guy who came up with patterns. Yes, it is. And so he talks about this idea of a city not being a tree. What does he mean by this? What we're talking about here is the tree of his title is not a green tree with leaves. It is the name of an abstract structure, which is brilliant because the minute he says abstract structure, it's just like, oh yeah, we have trees in software, because you weren't even thinking that it might be a green tree, because everybody in software knows what a tree is. Its root is at the top, the leaves are at the bottom, and if it's going to have any colors, then it's going to be red and black. Yeah? And then somebody says, no, I mean, like the trees outside, the green ones. Oh, that's funny, those are like based on the data structure, but they're the other way up. That's a really funny coincidence in the name. But this is great, because you're clued into this. And he says, it is the name of an abstract structure. I shall contrast it with another more complex abstract structure called a semi-lattice. So in other words, we're in the space of graphs here. Both the tree and the semi-lattice are ways of thinking about how a large collection of many small systems goes to make up a large and complex system. And the observation goes that the semi-lattice is potentially a much more complex and subtle structure than a tree. What does that mean in practice? when people use words like complex and subtle, let's think about this from a sort of software architecture perspective and broader. In other words, an architecture of software architecture is the enterprise architecture that we might be considering. When people use words like subtle, that's never good. When people use words like complex, it's kind of like, maybe we could simplify it, make it nice and hierarchical. Maybe there's a simpler way of viewing the universe, something that will fit conveniently on my PowerPoint diagram, and so on. An easy way to draw something. In other words, we're looking, it's a very natural human instinct, we're looking for a simpler way of expressing or dealing with something. But the problem is that perhaps the complexity and the subtlety is a necessity in this case of what we want to express. It is this lack of structural complexity characteristic of trees which is crippling our concepts of the city. And he was contrasting, this essay was written quite a few decades back, he was contrasting that, the 1980s, which is quite a few decades back now. He was contrasting this with a very strict, if you like, high modernist view of how to structure a city and its services, very zoned and so on. And as he points out, well, a city and the places in which we live are a reflection of who we are. And curiously enough, this actually works with software as well. He makes the observation, the reality of today's social structure is thick with overlap. The systems of friends and acquaintances form a semi-lattice, not a tree. We see these oversimplifications into tree form in organizational structures. Does anybody work or has worked in an organization where they have an organogram that is beautifully hierarchical? It's a nice tree, and up at the top there is the CEO. And down at the bottom at the leaves is where the work happens. And then somehow it's a system of routing water from one to the other, I think. The flow of currency or belief. Or the vision statement, that's what flows through an organizational tree. But if you actually look at how people work together, if you actually look at their communication patterns, it's subtle and complex. And when people work together to create software, it is relatively unsurprising when we discover that their actual relationships are impressed upon the image of the software. And this was originally observed by Melvin Conway in the late 1960s. That notion, it's very natural for the communication paths within an organization to be reflected within the software structures we create. It would almost be unusual if it were not. That is neither a good thing nor a bad thing, it's just a thing. So if we have all these incredibly rich structures, and we oversimplify them, there is a consequence. If we oversimplify our views of them, there is a consequence. There is going to be inevitable friction. If the simplicity of structure, the tree is comparable to the compulsive desire for neatness and order that insists the candlesticks on a mantelpiece be perfectly straight and perfectly symmetrical about the center. Okay, I confess, I would line up the candlesticks like that. But we're not lining up candlesticks, we're talking about something far, far larger. That sensibility is not unreasonable locally, but how does it work in an organization? We're not talking about pieces of code that are, school projects. We're talking about something much, much larger. How do we maintain a strict mantelpiece tidiness over an enterprise architecture? Or is that perhaps the wrong way of looking at it? The semi-lattice, by comparison, is the structure of a complex fabric. It is the structure of living things, of great paintings and symphonies. Now, you see, we always like it when somebody draws a parallel, and I'm kind of vaguely hinting here, aren't I, that what you do is paintings and symphonies, and with the word great in it. Maybe. But what he is observing is there is a challenge here. The tree view is simple for us to understand, but actually is in conflict with the nature of the thing that is being built and the nature of the way that we work. So perhaps we should embrace the complexity and subtlety and seek out alternative means of expression. Now, we could actually run a full day on the consequences of this. Sadly, we do not have a full day, but what I'm going to do is we're going to sample at this point one particular worldview and set of architectures that does fit into this kind of idea. That goes the opposite way from, well, we hope for trees, we get monoliths. Or perhaps we should be looking at microservices. So I'll hand back to Randy Shoup.
Great, so I wanted to talk about evolution of architectures from monolithic to more microservices style. So we're probably all familiar with this. You know, the true monolithic architecture is sort of a single vertically integrated unit, and you know you're talking about a monolith when people use the words like the system, right? Okay, we can do slightly better than this. Sorry. We like to often, not prefer monolithic architectures, but the reality is that there are plenty of pros and cons, and there are really trade-offs to everything. So the pros are a monolith is very simple at first, right? In fact, if you were a startup and you built a microservices architecture with 3 people, like I don't think you're spending your effort in the right place. It's very simple at first to build a monolith. We can all hold it in our head. Latencies between parts of the system are in process, right? So you get full memory latencies, full speed back and forth within, the single process typically that's a monolith. It's a single code base, it's a single deployment unit. That has very nice simplistic properties. And also, again, at small scale, it's extremely resource efficient. It's not like I need 20 different machines, each doing a little bit of work. I just have maybe one machine or hopefully some replicas, but one set of units that are responsible for the monolith. Now, there are some downsides, and it's worth saying a few of them. One of them is, of course, coordination overhead. So as more teams are more pieces of your team, more individual developers are synchronizing on updating that same monolith, that overhead, to the point of Amdahl's law, grows up. Poor enforcement of modularity, right? So we all learned, I hope, in university about modularity and encapsulation, and we know that this is a good engineering practice. But it's nice if the system helps to enforce that. So one of the things that the monolith does not do, even if you're well-meaning and intending to write modular and encapsulated code, you can cheat without even knowing that you're doing so. Poor scaling, right? So as the team grows, as the usage of the system grows, you really can only scale a monolithic system in a vertical way and not in a horizontal way. On the deployment and build side, it's all or nothing, right? So if there's some problem in deploying the new version of the software, you might have downtime in your system. There will be failures in deployment and build will be more of a problem than in an architecture that's more divided. And then, long build times. Great. So we can do a little bit better than this. And this is sort of the state of the art of enterprise architecture as of maybe the 90s, and probably a lot of our systems are still built like this, right? So I like to call it a set of monolithic tiers. So, okay, we've divided along these tiering lines. So we might talk about the front end, which is, a presentation tier. We might talk about the middle tier or the application tier or the business tier. And we might talk about the database or the persistence tier. Great. The big problem of, we can talk, this isn't such a, this is an improvement, but the issue tends to be around the monolithic aspect of the database, right? Because typically the front end and typically that middle tier can be horizontally scaled because they're typically stateless. But the monolithic database is where the monolith part still, lives in this architecture, right? So again, what's great about a monolithic architecture is it's simple at first. Join queries are really easy. So all the data is in one place. I can just write a complicated SQL statement to relate any of the entities that I have in my system. It's typically a single schema, a single deployment, single upgrade. So from the perspective of manipulating the database, it's relatively simple to do. And again, at small scale, it's pretty resource efficient. Again, similar problems to when we have the whole system in the big box. Major coupling over time, right? So you end up coupling together in unintended ways queries and interactions between the different entities in your overall system. Very poor scaling and very poor redundancy characteristics, right? So I'll use the example of eBay, but you can think of examples in many of your organizations. At eBay, users grew at a certain rate, and items, things you could buy on the site, grew at yet another rate, and transactions, people buying items, grew at yet another rate. So in the world when that was all in one monolithic database, we could only, the different entities couldn't flex at the right, it couldn't scale independently of one another, and we could only grow the whole big thing all at once. Because of that, it's difficult to tune one of these monolithic databases very well, right? Because we have a bunch of workloads that are around dealing with the users, a bunch of workloads maybe that are dealing with the items and with the transactions and with the other entities that are in our system, and it's difficult to tune the database properly for all those different styles of workloads. And then finally, the schema management of this is sort of all or nothing. So almost every large-scale organization that I'm familiar with has ultimately, independently, come up with something that ends up looking more like what we're calling microservices now. And they've all suffered sort of the same issue of first the monolithic system and then the sort of tiered system, and have all independently sort of invented something that ends up being pretty similar. So microservices are, again, single purpose. So the individual units tend to be very single, a very kind of small, simple, and well-defined, or simple with a well-defined interface. Here's modular and independence, writ large in the architecture. So the individual services are very sort of modular, and one hopes you can combine them in very interesting ways. Again, along the lines of sort of the semi-lattice, right? It's more about a graph of relationships than it is about particular tiers or a particular hierarchical organization of the services. And just to sort of give you a sense that this isn't really a new, this might be a relatively new word in the last year or so, but it's not a new concept. And this is just the fullest expression of, again, the standard techniques of encapsulation and modularity that I learned 25 years ago at university, and probably you all did too. So the thing that I want to sort of highlight here is the critical thing about making microservices work properly, and this echoes something that Adrian Cockcroft said in his talk several hours ago, is that the persistence for each of these individual microservices needs to be isolated. Because if you just have a bunch of individual services, but they all end up talking to the same database, that's not independently deployable. They're still very coupled to one another, both in performance characteristics and often in functionality. So the trick to making this work, almost the most important thing to making this work, is that each of the individual services owns, for some value of owns, its own persistence. Great. So as with everything, pros and cons, right? So some of the pros of this architecture are each individual unit is relatively simple and can be built by a relatively small team. And if you have to rewrite it, it can typically be rewritten in a relatively short period of time. Now that we have these individual services, we can do independent scaling and independent performance tuning on them individually. Also, and this is not a small benefit, because they're simple and because they have well-defined interfaces and because they're modular and independent from one another, now we can independently test those things and independently deploy those things. So even if there weren't other organizational benefits to this type of approach, simply the ability to test and deploy these things independently is itself an extremely valuable benefit of this approach. And then finally, as I mentioned, we can optimally tune the performance for those individual services. And I'll take the example of, many times over the last maybe 10 or 15 years, I've had the experience of attempting to insert a caching layer for read performance between a monolithic database and the rest of the tiers of a system. That typically is very difficult to do. I hope, if you've tried to do it, I hope you've been successful, because I never was. And that's because of the very different workloads and all the different dependencies that you have to model in the caching layer to make it behave as if everybody's talking directly to the database. Well, once you've broken everything up into microservices and everybody's talking to that entity through only the microservices interface and through no backdoor mechanism, now you can cache and performance tune those individual services to your heart's content. And it's a lot easier, right? Because typically you're not trying to maintain a bunch of relationships in that cache and do a bunch of cache coherency issues. You simply have to do a very simple caching technique around sort of keys and values, if that makes any sense. Great, so those are the wonderful things about a microservices architecture, but let's not pretend that we haven't given a bunch of things up. So we have many cooperating units. So now the organization has to support that, and now there's just a lot more individual things going on in the overall system. Typically, to make this work, we all have many small repositories of code, so it can sometimes be difficult to get an overall view of the overall code in the entire organization. This isn't usually that difficult, but if I want to search and replace everything for a particular bug or upgrading to some new version of Java or whatever, that's a little bit harder to do piecemeal than it is if I had everything in a single code base. And of course, let's not forget the critical aspect here is that it requires a bit more sophistication around tooling and dependency management between the individual services. And then finally, last but very much not least, Now that we've introduced a network between these individual components of our system, now we're suffering the latencies there, right? So it's no longer in-memory latency between the components of our system. Now those latencies are over the network, and it's very much more important to call things in parallel, be asynchronous, be non-blocking, and so on about those things. So it does impose some non-trivial sort of requirements on developers of development of good solid microservices. So I want to give a specific example very quickly of something that we did at Google. And the details aren't super important, but I just want to show this is what this is what a slice through a microservices architecture that's pretty mature looks like. So I'm not selling this, but I happen to work on it. Part of the cloud platform, part of Google's sort of platform as a service, is something that's called the Cloud Data Store. And the details aren't important, but it's a pretty large hosted NoSQL system. That is something that's leveraged by external developers not working at Google. And it has various interesting properties. So it's extremely highly scalable. It's got strong transactional consistency, which is relatively rare in these very large-scale NoSQL systems. And it's got pretty rich query capabilities that tend to be pretty similar to SQL in a lot of instances. Great. That's built by a team of 6 or 8 people. That's it. Right below that is an internal service called Megastore. There's a paper about this, so I'm not, feel free to read that if you're interested. That gives the capabilities of a geo-scale, a regional sort of continent scale structured database. It has the capability to do multi-row transactions, and it does synchronous cross-data center replication within a region. So writes that go to one data center will get immediately replicated and acknowledged by the other replicas that are in those multiple data centers. Great. Below that is another, and that team is 6 people worldwide. Bigtable is, again, there's another Google paper about this. It's cluster level structured storage. So within a data center, it's a sort of key value store on steroids, and maps a row and a column and a timestamp to a particular value of cells. And Bigtable is used for basically everything at Google. So anything you would use a database for is built on, typically on top of the Bigtable service. Bigtable itself is built on the current version of Google's file system called Colossus, and that does, again, at a lower level, a distributed file system, block distribution, block replication, that type of stuff. And then finally, everything at Google is built on the cluster management infrastructure, which does task assignment and resource, sort of machine resource allocation. And when machines fail or processes fail, it knows what to do. And the point is not any of the particular details here. I'm not suggesting that you need to build this system, but this is what a large-scale microservices-based system ends up looking like at scale, right? It means you have you can see, if you kind of roll it up, you can see that each of these units does a very distinct, very clean set of functionality, and you can see how the level above it is, sort of built on top of it and adds another incremental capability. So a few pro tips. Now you want to build some microservices. Randy, can you give me some tips? Sure, happy to do it. So the first thing that has been done at all these places, sort of Google and Amazon and then Kixeye, the gaming company that I was at until recently, have typically built what I like to call a chassis. So a common set of underlying pieces of componentry that help you build new microservices. Things like monitoring hooks, client-side load balancing to downstream services, et cetera. And I just need to give a shout out to the Netflix folks, because at Kixeye at least, we leveraged a lot of the excellent open source work at Netflix to do all this. The first thing we should do before build a microservice is to define the service interface in a formal way. Talk to your customers. I don't have a customer yet. Great, then don't build a service. Talk to the customer, minimum one and hopefully several, and define as a conversation back and forth with those customers the absolute minimal interface that gives them what they need. Propose it, discuss it, and agree upon it, at the sort of 50,000 foot level. Actually, not even the 50,000 foot level. At a formal level, I'm going to pass you this. You'll pass me this. I'll give you this back. Then I recommend prototyping and implementation. Right? So do the simplest thing that could possibly work. The client can now integrate with that prototype because it's something that's working, but maybe it's not that fast, and maybe it's not that scalable, and maybe it doesn't deal with failures all that particularly well. But it's something that everybody can get started with on both sides, right? So the client gets to integrate with something that actually works, even if it's not the permanent system, and the implementer can learn what works and what doesn't work back and forth with the client. Then I recommend throwing away completely that prototype, right? Having the discipline to throw away that thing. And it's so hard for management. Sometimes I wear this hat myself. It's so hard often for people to understand that it's actually easier often to throw away the thing and build a new thing up from scratch than it is to go back through and retrofit the thing that we built in 2 weeks or whatever. So I strongly recommend that for the real implementation, you have the discipline to be willing to completely throw away the prototype. And then rinse and repeat, by which I mean do this for the next service and the next service and the next. So the final set of things I want to talk about here is what this implies about teams interacting with one another in a microservices situation. So again, I think has been said in many ways in this conference, but I'll say it again in my own words. Again, in that hierarchy that I showed from Google, the discipline there is that each of those interactions between, for example, the cloud data store team with the megastore team, the megastore team with the big table team, et cetera, we work at the same company, but we want to have a formal discipline around that's more like a vendor-customer relationship, right? So we should be friendly and we should be cooperative, and we're all trying to help one another and make the business be successful. But we need to be structured and disciplined and sort of principled about those interactions. So in particular, we need to be super clear about the ownership and about the division of responsibility between sort of who does what across this interface. And here is maybe the most important discipline that's, again, very difficult for managing folks to accept. Even though I built it on spec for that customer, the customer, just like for a third-party vendor, the customer should be able to choose to use my service or not. If we don't have that situation, it doesn't put the right incentives on both sides. Do you see what I mean? I, as a service provider, should be competing, if you like, just as much with the customer might be able, my client might be able to do the thing that they asked me to do better than I can. Great, they should have that opportunity to do it. There might be an open source project or a third-party vendor that they can use, which is overall cheaper or better or faster or more beautiful than what I provided for them. And we need to give those customers the ability to choose that. If we don't, then we've almost forced an inefficiency and forced an incorrect kind of set of incentives in the organization. So again, a way to make this a little bit more formal is having service level agreements, whether they're formal or, depending on how formal you might want them, but service level agreements between provider services and consuming customers. And obviously those should talk about promises of service levels by the provider. So if you call me 10,000 times a second with 10,000 or 10K request sizes, then you can expect a certain response latency at the median of this and the 90th percentile of that. So we have an agreement, a set of expectations back and forth on what it means to have a well-performing, reliable system. And we do this not just for fun, but we do this because the customer needs to be able to the customer of my service needs to be able to rely on the thing that I build as if it's a service, as if it's a utility, right? They're building their very important business stuff on top of mine, and they need to be able to rely on me. And then finally, and this is sort of in an increasing order of sophistication, once you have gone sort of all in toward this sort of microservices and very highly componentized architecture, you're going to end up, for economic reasons, wanting to institute a sort of charging and cost allocation model. And this is not unfamiliar to traditional businesses, right? It's very common to have internal balance sheets of allocated costs between different business units and so on. But it's important even in the technology world because customers ought to be charged for the usage of the service. Actually not because I feel that I desperately need to be paid, but because it aligns the economic incentives, again, between the customer and the service provider. So if a customer isn't willing to pay, either in real money or in funny money or whatever, if they're not willing to pay me for my service, maybe I should do something else. Does it make sense? Right? If I'm not providing a service that's worth paying for, just like a startup, just like a vendor, You know, I should go do something else and contribute to the organization in a different way. Similarly, if a customer is paying to use my service and paying by usage, they have a good incentive to properly minimize and optimize their usage of it. Does it make sense? If it's completely free, then I don't know, why don't I call the service once a second, 1,000 times a second, 1,000,000 times a second? It's totally free. But now if we start to charge for usage, then the customer is appropriately incented to make the right trade-offs and optimize that appropriately. And the little, I won't say too much of the detail here, but there is a particular example in my experience at Google where there was a service that I was in charge of providing, or my team was in charge of providing, and there was another customer group elsewhere, and there was not a charging and cost allocation agreement in place. And that customer was able to use 50% of the resources that I had allocated to this particular service globally. So that's a pretty significant feat when you're talking at Google scale. So they were able to do that, and I mean, they were nice people, but hey, they had their other priorities, right? They had stuff to do, and their first order priority was not make life better for Randy. It was to help their own customers. So they were, you know, they were properly, they were incented properly, or they were following their incentives properly. But once we instituted a cost allocation model, somehow magically they were able to reduce their usage by 10%. You know, so they were using 100 units, and then all of a sudden they were using 10 units. Something they said they couldn't do before. Great. So that's all I have to say about microservices. Again, if we could hold the questions till the end, very happy to talk here and later about these things. So thank you.
Thank you very much, Randy. And I know for a fact that that's not all Randy has to say on microservices. So I tweeted this a while back. Because one of the things that we find is when things become widespread and popular, you move from the early adopter stage, which is refined, sophisticated, profound, and deep understanding, and then everybody else gets to use it. And it's never quite what you envisaged. Object orientation. You know, I don't remember there being, you know, factory manager proxy controllers being part of the vision of objects. But that has become a standard fit way of doing things, to sort of say, oh yeah, we've got an object model, and you go through it and you say, well, I'm seeing lots of infrastructural names, and yep, we use a standard naming convention and we glue everything together. It's kind of like German, you know, it's, yeah, fine. But really, that's not a generative architecture. That's not what we're talking about. And sometimes people with short memories, or perhaps not enough history, say, well, you know, we're going to move on to another paradigm, and that'll solve all of our problems. Believe it or not, you can actually write good procedural code. So when everybody was going around going like, oh, objects, that gets rid of the procedural problems that we have. Yeah, no, what happens is that people who are writing bad procedural code follow in a few years later. Guess what's going to happen to functional programming? Large functions with lots of side effects, and they're going to be called imaginative things like function and transform and process and calculate. In fact, brilliantly enough in the break, Ola Bini came up with the idea of, yeah, well, what about actually when people start mixing their paradigms? They mix functional, they mix object. We're going to end up with these people writing monad factories. Yes, that might actually become a real thing, and yes, you should be afraid. However, it doesn't have to be like this, and we're going to do the one hardware switch in this talk. It doesn't have to be like this, and I'd like to introduce Ola Bini talking about, and you get that bit, polyglot programming, which we often think of as, well, it's kind of nice if you're doing your own environment, you've got complete control, but actually, no, I think that's everything. Yes, good. Okay. I'm going to let him take it away.
Yes, I'm going to take a slight step away from the enterprise environment and talk about. Well, first of all, I want to have my slides working. That would be good. So I want to be talking about polyglot architecture, and the cables just keep going. Okay, sorry about that. Okay, now we do. So, I want to talk about polyglot architectures, and this is something that has been coming more and more the last few years. A big driver in this has been that we now have environments where it's actually possible to run a lot of different languages in the same environment. The JVM, the CLR are big drivers in this. Of course, you're all polyglots already. If you're a developer right now, you have to use a lot of different languages to get something done. Almost every developer knows how to do at least SQL and probably some HTML, probably some JavaScript, probably some Java, and so on. However, what I'm talking about and what I'm going to talk about is more consciously choosing to use more than one language, not because they are the only language in a specific environment that is reasonable to use, but because you actually want to utilize the specific characteristics of a language to get real benefit. So not using SQL just because SQL is the only choice you have for the database, but using, I don't know, I don't even know if CoffeeScript is a good example as a language because it's close enough to JavaScript. But I'm going to give an example in a few seconds. So a polyglot architecture is really just an architecture where you consciously combine languages. And you can use them for many different cases. I've used them most of the time when you deal with problems that are complicated. Then you have to go away from Java and you have to take on something better. Or conversely, when you're dealing with problems that are easier than usual, then going to something like Rails or something like PHP to get a really quick start. There's a whole bunch of different constraints like that you can use. However, there are also costs, of course. You can't just pick up several languages and put them into the same project and hope that everything is going to be fine. So this is something you have to choose to do consciously. You have to know that picking up a language for people usually takes some time. It usually comes with an improvement ravine where people will not be as productive as they used to be for a while. But if you choose them correctly, then they also have a lot of benefits. I often get the question of how you choose them, and that's one of those problems where actually experience is the right choice. You just have to be an experienced developer, you have to try different languages, and you have to know, you have to have a feeling for what they're good at. There are a few patterns that I've seen or used in different ways and how you use them. And taking from Randy's, microservices is one of the best ways of just using languages to their benefit. Most of the projects I've seen the last few years end up having at least one or two services that are written in different languages and so on, depending on what is right for the specific behavior. Another thing that I've seen in more monolithic applications is something I call the inverted pyramid. And the inverted pyramid is this way of structuring an application so that you have a core of services to the application that is implemented in a static language. It's a small amount of code because it doesn't have to be big. It's stable, you don't touch it very often, and it provides the services to the rest of the system. On top of that, you build a slightly broader layer in a dynamic language. And then finally, on top of that, you build most of the business functionality in one or several domain-specific languages that you created for the specific purpose of implementing the language. Implementing the application logic. And this kind of structure works really, really well on the JVM, for example, where you can use as the base layer something like Scala or Java. On top of that, JRuby or Clojure, and then on top of that, a DSL of some kind. Now, auxiliary services of different kinds. When you do the most of the processing in one language, but kind of offload, say, data processing to another service is also something I've seen. The Emacs model of end-user scripting, where you have a base language that implements the core of the application, and then you expose scripting to an end user, is also quite common in some settings. Of course, in Emacs, you can see the kind of the extension of this, where actually most of the application itself is written in the same extension language as the extension language that is offered to the user. And this provides a whole bunch of power for the right type of application. And finally, you also have domain-specific languages where as I talked about earlier, you can create a language that makes it easier for you to express your domain concepts. And then you implement the application logic in that. Now, under auxiliary services, the other thing you can do that is also very, very common is to do testing using a different language, or alternatively doing build scripting in a different language. We have some very, very conservative banks and investment banks as clients, and even in those settings, we're now in a situation where our .NET projects are using build scripts implemented in Ruby, because it's just such a big difference to do that kind of thing. And the same thing is true with testing. Testing using a language like Ruby, even if your application code has to be in Java for various reasons, you can still get a very, very large performance benefit from testing in Ruby, or any other language really. Groovy works really well, and so on and so on. Since you write less code to test, that means that you can have better structured tests, you can have more tests. And the other thing you can do that is also quite common is to use another language in order to do feature level testing or acceptance level testing, using something like Cucumber to drive a browser. And that kind of scripting happens very often in something like Ruby. Another typical example is scripting your infrastructure. I'm sure everyone in this room have complete self-serve environments, so they can recreate their environments from scratch without having to do anything manual, right? Doing that is something that is dependent on languages as well, and my experience has been that using something like Python and GOTO and Fabric for setting up new environments, and then running Puppet or Chef or Ansible on top of that runs really well. So there is also another thing you can do, which is language migration. If there is value, don't stick with a language. If there is value in switching, and this is going to be a long-term project, or think about the fact that most projects stay in maintenance much longer than they're being developed. So in 2 months into a project, if you realize that you're actually using the wrong language, you might actually consider to switch. I'm going to talk about a project where we did this, where we basically ended up rewriting all of our JavaScript code into CoffeeScript. And that was a small step, of course, but it was still one of those things that made the code much more maintainable. Okay, so based on a real project, I just wanted to very quickly talk about one project I did many of these different things, and where it was absolutely crucial for us to be able to do what we did. This was about a 1-year project. We were 4 or 5 developers. I was the most senior on the team, but and we had 2 fairly junior people. So it was a very varied team. Now, we used most of these techniques, and the problem we were trying to solve was basically cancer treatment. And so I'm going to give you a very, very, very quick introduction to the problem. So genomics. Actually, let's just talk about the scale. You've all heard about DNA and genes and so on. We were trying to figure out, based on sequencing of genomic data, how to best treat cancer. And sequencing is really the idea of taking physical matter of DNA and turning it into bits. And then once you have those bits, you have to do analysis. But the problem is that doing this analysis is extremely expensive. And the reason why it's expensive is because the human DNA, the human genome, is very big. It turns out that the complete recipe for one human being is 3 billion base pairs. And what makes you you, compared to any other person in this room, comparing 2 people, is about 5 million mutations. And then you have about 100,000 proteins that make you do whatever you do, and roughly 21,000 genes. And after you sequence a genome, you end up with a file that is roughly 0.5 terabyte in size. That was kind of the scale of the problem. Except, actually, we weren't dealing with 1 sequence. We were dealing with 2 sequences, because you have to sequence the normal genome of a person, and then you have to sequence the cancer genome, and then you have to compare them, and then you have to try to figure out what is actually going on in the cancer that is making it into a cancer. And once you can pinpoint that, then you can start trying to figure out, okay, is there anything here we can target a treatment on? So traditionally, so cancer is this weird thing. It's not really one disease. It's 10,000 or 100,000 diseases. It's really something that goes wrong in your genome, And it can go wrong in many, many different ways. And once it's gone wrong, the genome starts getting more and more wrong. So it's very, very hard to actually find what started the cascade of wrongness in a tumor. It's also really, really problematic to treat it. Right now in the US, the situation is actually really stupid. The way it works is, say if you happen to be a woman, which is not very common in this room sadly, and you get ovarian cancer, at the point you get the diagnosis, you have much higher than 50% likelihood of being dead in a year. That's how bad ovarian cancer is. Now, you go to the doctor. In the US, there is something called standard of care, which basically says that these 3 chemos are the first-line treatment for ovarian cancer. How does the doctor choose? Well, he has no actual rational way of choosing between those 3. The 3 chemos are very different in the effects they have on different types of ovarian cancer, but the doctor has no way of knowing which type you actually have. So he chooses one based on what the hospital usually uses, or he chooses based on what the insurance company decides that they want to pay, or he flips a coin, basically. And then you get this chemo, and that takes roughly 3 months of time. It costs roughly $100,000, and you're dealing with extreme pain and suffering for 3 months. And if you have ovarian cancer, that's 3 months of that maximum 1 year that you have likely to live. And if it doesn't work, he tries the next one, and then the next one. And that's really the treatment problem. And that's why we need very urgently to take all this information that I talked about and start applying that to decide what treatment option is actually the right one to do. So that was basically what we were working on. And we ended up with an architecture that had a single page front end. So the front end was the least interesting part. It was basically just displaying a little bit of data and a few graphs. But we ended up writing a single page front end using JavaScript that we later switched over completely to CoffeeScript. And it communicated with the backends only using RESTful interfaces. And we implemented several services in various languages. We had a core that was implemented in Clojure. And we had roughly 10,000 lines of Clojure code, which is quite a lot of code, but we had to model a whole bunch of biology in order to get to the point where we could actually draw useful conclusions about the cancer. But we also had to take in millions and millions of rows of data from public databases all over the internet. We needed databases of drugs, we needed databases of genes, we needed databases of proteins, and we needed 3 or 4 of them, because as it turns out, all these databases, I was absolutely shocked to find out that these databases with biological data that a lot of doctors depend on, they're not very clean. They contain a lot of really dirty data. It's really, really bad. So we ended up having to do a lot of data munging, and we had to do a lot of combining of data and trying to figure out, okay, combine these 3 data sources, can we get a data set that is good enough to work with? And Ruby ended up being the right language for doing that kind of thing. So we had a significant amount of Ruby code that was very, very good at just taking data in whatever format we threw it at and output something that we could use from the core of the system. In fact, it turns out our Ruby code actually had a very strange feature. They were implemented as microservices that did all the parsing and munging. All the different data points came from different microservices. However, the output of the Ruby code was actually Clojure code that knew how to put itself into a data storage. So our Ruby code generated Clojure code with the clean data. We ran everything in JVMs. We had probably 20 different JVM instances running in the final system that was communicated with each other. And we had a graph database that was the glue that bound all of our data together into something that we could actually use to draw conclusions. So polyglot architectures are really powerful. I think that people should investigate them, and the precursor, in order to use polyglot architectures, you need to learn languages, you need to expand your mind, and you need to go out and not just learn C# if you know Java, you need to actually go out and learn Smalltalk or Prolog or APL or Lisp and so on, so you know what's out there, or Erlang for that matter. I'm a strong believer in using the right language for the job. A big part of this is having developers on your team who are developers. You don't want to hire Java programmers, you want to hire programmers. And if you have the right people, then picking up languages for the right tool, for the right task is actually something that you can do. Choose languages consciously. Another lesson that is not really relevant to this architecture thing is that we were a very small team, and that worked out much better than having a large team would be. And I found in my experience that small teams actually perform better and can do things that large teams usually can't. So, thank you. Yeah.
So as you can see, I'm Kevlin Henney now, because he had to run to his flight. But thank you so much for attending. Now we're at the place where we can ask questions as far as you'd like to stay. And we actually have two online here for Randy. We can start with those. So the first one is, isn't microservices just a new buzzword for software components as defined by, and I clicked away.
Yes.
Hang on, there were two names, they were really good. As defined by Palmas in the 60s and Zispersky in the zeros.
Sure. So I don't know the references, but I'm sure you're correct. No, like I was trying to hint, it's just a new word for the common good engineering practice of good encapsulation and well-defined interfaces. And we do this at different layers, right? Inside our code, if we write object code, interfaces that we have to our objects are, we hope, well encapsulated, and there's no secret way to backdoor get into that object. We do the same thing at a higher scale, all the way at the other end at microservices. So yeah, it's just a reflection of good engineering practice.
Thank you. And the second question, actually, it got kind of answered by Ola, but I'll still ask it. Doesn't a common chassis lock down an organization to a single platform or language? Java, C#, Ruby, Erlang, etc.
Yeah, no, that's an excellent question. So does a common chassis, that underbody of a service, doesn't that lock it down to a particular maybe set of languages? I mean, in the particular case, we happen to use the Netflix open source stuff, which is written in Java, and since it's on the JVM, it works well for Java and Scala, and those were the languages that we used. There's no, so along the lines of Polyglot, I guess the way I would say it is, let's imagine that we want to do some things in JVM languages and then other things in, Erlang. It's another VM, Erlang. One would make sure that we had the same requirements on the microservices written in the JVM languages versus in Erlang, but the implementations might be different. In fact, we probably would be different, right? And as people who are familiar with Erlang, a lot of the things that actually we attempt to do with the chassis actually wouldn't even be needed to do because they're just naturally part of Erlang. Anyway, so absolutely that's true. But you know what? This is very analogous to the metaphor that I'm trying to use with a chassis, which is, again, a chassis is the underbody, the foundation of an automobile, and most car companies have a very small number of chassis, but a very large number of models, different kinds of cars built on the same chassis. No car company that's very large that I'm aware of has only one chassis. The analogy works well, thank you.
Thank you for that answer. And then a question I think everyone is kind of curious about, the cancer project, how did it go?
When we left, it was in production for ovarian cancer, and they were doing clinical trials on it to see how well it performed. I haven't heard anything since, but as far as I know, they're still working on that. So hopefully it will go somewhere. I think this approach that I only very briefly described the approach. The problem with cancer and genomics is that we still don't really understand DNA. We still don't really understand most of what's going on in the inside of a cell. Once we get to that point, we can solve cancer permanently. I don't think that's going to be a problem. But that's going to be 10, 15 years off from now. And I think until we get to that point, this kind of approach, which is actually using big data analytics on a lot of existing material out there, is probably the only way I can see of solving this problem.
No, I couldn't agree with you more. I work with a lot of customers and research centers that do this kind of combine different data sets to get to answers quicker, especially in the cancer research area. So I'm very intrigued by these kind of stories. I'm sure you are too. Any other questions? I'm going to move forward so I can see you. Yes.
So one question relates to costs, because you said procurement and it's much easier for a developer. Quite often I've seen the developer that needs the stuff does not have the power to buy these kind of cloud services, because he either puts it out of his own packet or he goes to the procurement again through all the cycle. I need the money to buy this service to do that, and it's just moving the problem somewhere else. Don't you think?
So I think that question is for you, Randy, on cloud services and how it could be accessible or not for developers with limited resources.
Yeah, sure. Well, typically I have several answers. The first meta answer is that I will answer your specific question, but the meta approach is I personally believe that teams should be responsible end-to-end for the things that they build and for all the costs that they incur. And those are different, and that again is one of those things about, maybe you can see this sort of underlying theme to a lot of the things that I say, which is trying to set up the proper incentives so people naturally behave in the way that we want and optimally. And that's another, in the same way as we talked about microservices, where, somebody who leverages my service ought to pay for it. Again, that gives me good incentives and them good incentives. Similarly, I as a producer of a service need to be held responsible for the cost of my service, because again, I should be driving that down. Okay, so that's the first order thing, is make sure the costs that any team or person is incurring is in some way part of their responsibility and part of their, accountability, right? I've worked at very large organizations as well, and lots of times the procurement policies are really difficult, and we have to say, a year ahead, 2 years ahead, all the exact things that we want to buy. That is a real challenge. I mean, I'm not going to argue that there's no secret back door. But honestly, cloud services these days, particularly for something where you're playing around, is petty cash. Like, it really is so small. And, obviously when you get large to be, Netflix scale or Pinterest scale or something like that, then the bills are ordered, are measured in tens of thousands, hundreds of thousands, millions, and tens of millions of dollars. But then we better be budgeting no matter what, right? Yeah.
Okay, if there's one last question. Okay, good. Thank you.
Can I make a last plea?
Oh, yes.
So, I promised this to Tim Bray last night. So I hope everybody attended Tim Bray's opening keynote of this conference, where the very first set of words out of his mouth were, we really ought to do a better job in our industry, and particularly in our conferences, about having a more diverse viewpoint, like fewer people that look like me and a lot more people that look like Eva and look like other folks. Let's do what we can. Not necessarily sure that I know the solution, but let's go back to our organizations and see if we can get more people that look less like me and more people that look different. And I'd love to be able to look out next time I do this conference on a sea of, multiple genders, multiple races, multiple sexual preferences, et cetera. That'd be a lot more fun, a lot more diverse. And frankly, we're leaving, if we think nothing more than, about we deal in ideas. And we're missing out on a lot of ideas by not being as diverse as we could be. Thanks.
Thank you.